Okay, so in this video, I'm just going to go through the beginning of the quantization of the Dirac theory. So to do that, we can work very similarly to how we did things with the complex scalar field. So we're just going to take our Lagrangian, and we're going to find the conjugate momentum, and we're going to assume, for the complex scalar field, we assumed the canonical and commutation relation. This time we're going to not do that, but we still need the conjugate momentum, which will be I psi dagger. And our expansions for our fields, it's going to look kind of similar to the complex scalar field, only this time we're taking inspiration from what we found last time. So remember, last time we found that we could form solutions to the Dirac equation out of these basis spinors US and UR. And so any linear combination of them would be a solution of the Dirac equation. And that's why I have basically this linear combination here. And then similarly for these V spinors. And then we can write that in a more compact notation like this. So I have two S's here, so there's an implied sum over S. And then, so that's psi, and then psi dagger will just be the Hermitian conjugate of that, so that's easy. And what we're going to do, instead of demanding that our field and conjugate momentum satisfy commutation relations, we're going to demand they satisfy anti-commutation relations. So basically psi and I psi dagger should equal, the anti-commutator of those should be I delta x minus y. And obviously the i's will cancel, so I just end up with this relation. So we want to make sure, just like we always do, that if we have these expansions for our fields, that they satisfy this anti-commutation relation. And we're going to do that is the same thing we did last time. We assume that our creation and annihilation operators obey these anti-commutation relations. So this is for the B's, but obviously the C's will satisfy a similar kind of relation. And so now we can compute this commutator here. So I end up with this double sum, this integral over P and Q, and it's not too hard to work it out, but basically, so you basically end up with commutators of all these things. It's kind of like foiling. But the commutator of B and C will go away, commutator of C dagger and B dagger will go away. So the only terms that contribute are the ones that have the anti-commutator of B and B dagger and C dagger. So I end up with this, and then I just use these relations. So basically, Q will become P, S, well, I've used Z here, but so Z will become S, and yeah, so it's not too bad. I end up with this thing. And then I can use, so last time I wrote down a few identities involving these spinor, our basis spinor contractions. So we had these outer product relations. This outer product is this matrix. And so we can use that to replace these things. So basically U dagger is P plus M, P cross plus M, and then V dagger is P cross minus M times gamma naught. So we get this. And now I can, here I just expand out. So there's the sum and this crossed P. It's, P contracted with the gamma matrices. So I split out the time and space parts. And now you can, because I have this integral over 3 momentum, I can exchange P, the 3 momentum P with minus P without changing the value of the integral. So I do that here. So basically this p becomes minus p, this p becomes minus p, so I can factor these exponential terms out. And then everything will just cancel besides my p naught gamma naught. And then this gamma naught will cancel. Well, gamma naught squared is 1, so that goes away. And then p naught is EP, so I'll have 2EP that cancels with this. And so I just end up with this exponential form of the Dirac delta. So our fields do satisfy the anti-commutation relation that they should, assuming our creation and annihilation operators satisfy this relation. So though I'll stop here for now, but next time we'll do the Hamiltonian.